Thank you for joining our presentation on understanding and constructing latent modality structures in multimodal representation learning. For a 1-minute quick overview of the paper, we study the impact of modality alignment with empirical and theoretical analysis. We propose 3 regularizations to construct meaningful latent feature structures, including intramodality regularization via deep feature separation, intermodality regularization via Brownian bridge, intra-intermodality regularization via geometric consistency. We demonstrate improved performance on both two-tower-based models such as CLIP and fusion-based models such as ALBEF on a variety of vision language tasks. The outline of this presentation includes background, analysis, method, experiments, and summary. Vision language pre-training aims to learn multimodal representations from large-scale image-text pairs. Many downstream tasks benefit from multimodal training, where aligning different modalities plays a crucial role for obtaining meaningful features. Typically, joint image-text models are trained with contrastive laws. However, in contrastive learning, image and text features still reside in different regions of feature space. Such a phenomenon is called the modality gap. The key question we want to ask is, with the existence of modality gap, how to better align modalities? We first consider, how about perfect alignment? Is this the ideal way to go? To answer this, we conduct empirical and theoretical analysis. Our empirical analysis shows that there is no clear-cut relationship between the gap of these two modalities and the downstream retrieval task performance. For theoretical analysis, we define an information gap to characterize the gap of information provided by two modalities towards predicting the target variable. We prove that using perfectly aligned features leads to an information loss of at least this gap. Our analysis indicates that features with zero modality gap can only preserve predictive information that present in both of the modalities at the cost of losing the modality-specific information. In other words, perfect alignment is not ideal. Now, to answer the key question, how to better align modalities, we propose instead of perfect alignment, we should use more meaningful alignment by constructing latent modality structures through different perspectives: intramodality, intermodality, and intra-intermodality regularization. Here's an overview of our method. We incorporate our method over the contrast learning framework. For intramodality regularization, we use deep feature separation by using a new feature to store the modality-specific information, and we optimize the new feature to be complementary to the original feature and meaningful. We use one projection layer to obtain the independent feature and use orthogonal loss to encourage the independent feature to be orthogonal to the original feature. We use contrast loss and uniform loss to optimize the independent feature to be meaningful. For intermodality regularization, we use Brownian bridge to connect two modalities. We use augmented features as the bridge to guide the transition between image and text modality. We optimize by aligning augmented image feature with the mean of the Brownian bridge. For intra-intramodality regularization, we encourage the geometric symmetry of the feature pair distances. We first enforce geometric consistency on the original features, where in the right figure, the equal signs of the same color indicating that we encourage this distance to be similar. We use cosine similarity to measure the distance. For example, we encourage the distance between image 1 and image 2 to be close to the distance between text 1 and text 2. We also enforce geometric consistency on the augmented image features. Similarly, for example, the distance between image 1 and image 2 is encouraged to be close to the distance between augmented image 1 and augmented image 2. We also encourage symmetry for cross-modal distances, such as between image 1 and text 1. This is an illustration of all geometric consistency laws we encourage. Our methods are general regularizations that can be applied for many multimodal frameworks. We evaluate our method on 2 popular vision language pre-training frameworks, including 2 tower-based models such as CLIP and fusion-based models such as ALBEF. Here are the experiment setup. We evaluate on zero-shoot transfer and demonstrate that all 3 regularizations can improve over baseline. We evaluate on natural distribution shift and demonstrate that all regularizations improve performance, while geometric consistency regularization has outstanding performance. We also evaluate on linear probing tasks and show that all regularizations improve performance, while deep feature separation regularization has outstanding performance. Here are a few visualizations of the results. We also visualize the latent feature structures obtained by different regularizations. For fusion-based models, we evaluate on visual question answering, visual reasoning, and visual entailment. We show that all 3 regularizations can improve the downstream task performance. To summarize, we study the impact of modality alignment with empirical and theoretical analysis. We propose 3 different regularizations to construct the better latent feature structures. We demonstrate improved performance on both 2 tower-based models and fusion-based models on a variety of tasks. Thank you all for coming, and here's appendix on the detailed proof.